A rotation is a transformation that turns a figure about a fixed point. We call that fixed point the center of rotation. When we're doing a rotation, we have two directions that we can rotate in. We can either rotate counterclockwise or clockwise. If the question doesn't specify which direction we're rotating in, it's assumed that we're rotating counterclockwise unless it specifies clockwise. Also, if it doesn't specify what the center of rotation is, it is assumed the center of rotation is the origin, unless otherwise stated. Keep in mind that when we rotate or turn an object, since it is turning, the direction that it's facing is changing. The orientation changes. Over here, I have an example of if we would take this smiley face and we rotate it 90 degrees counterclockwise, 180 degrees counterclockwise, 270 degrees counterclockwise. If we take the smiley face and we rotate it 90 degrees clockwise, 180 degrees clockwise, and 270 degrees clockwise, that is what it will look like. We'll come back to the rules in a minute. Let's take a look at some counterclockwise examples, and then we'll do some clockwise examples after that. So we're going to rotate this figure, this quadrilateral, 90 degrees counterclockwise. So remember that counterclockwise is the opposite direction from how the numbers on a clock move. So we're rotating this way. So right now this figure is in quadrant 2, and we're going to move it into quadrant 3 when we rotate it because we're rotating it counterclockwise. So what I'm going to do is I'm just going to dot my center of rotation, which is the origin, because if it doesn't specify, your center of rotation is the origin. And what I'm going to do is I'm just going to connect a pre-image point to the center of rotation. And notice how that's 1, 2, 3 down, and 1, 2, 3 over. Notice how we have an L shape over here. And I'll just redraw it on the side so that you could see it clearer. It looks like this. And if we were to take this L shape and rotate it 90 degrees counterclockwise, it would look like this. And that makes sense because if we go down and left, we'll be in quadrant 3, which is where we said that this point needs to land in the first place. So same movement, this was 3 and 3. So 3 and 1, 2, 3. And here we have our image point. I'm going to label that M prime. I'm going to write down the coordinates. The original was negative 3, 3. And the rotated is negative 3, negative 3. Let's check out point L next. And this L shape looks like this. And if I were to rotate it 90 degrees counterclockwise, it would look like this. This is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, and 1 over. So 1, 1, 2, 3, 4, 5, 6, 7, 8. And this is our point L prime. The original point L was negative 1, 8. And now the rotated point is negative 8, negative 1. Let's do point K next. Okay, so we could see that L shape. It looks like this, like a right side up L. And if we rotate it 90 degrees counterclockwise, it looks like this. It goes on its side. So this is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. The original point K was -7, 8. And now our rotated point K is -8, -7. And finally, all we have left to do is point J. And that L looks like this. So if we rotate it 90 degrees counterclockwise, it's going to look like this. And that's 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9. And then in the other direction, it was 1, 2, 3. And that is our point J prime. So the original point J was -9, 3. And now the rotated point is -3, -9. Let me connect my image points together so that way you can see my rotated figure. I'm going to use black to connect them. Oops, I connected that one. Not good. Okay, and here I have my rotated quadrilateral. Notice how it rotated 90 degrees counterclockwise. The whole figure turned 90 degrees in the counterclockwise direction. And now let's take a look at what happened to the coordinates. So what happened to the coordinates from the pre-image points to the image points is that they switched spots. Notice how -7, 8 became -8, -7. So the 7 and the 8 switched spots. And notice how the original y coordinate became the opposite sign. In all of them, the original y coordinate became the opposite sign. So going back to our rules over here for 90 degrees clockwise, they switch spots. Let me not use yellow for this. And the original y coordinate changes sign. Okay, next we're going to do a 180 degrees counterclockwise rotation. Remember, if it doesn't specify, it's counterclockwise. But if we look back over here on the smiley face, if we rotate it 180 degrees counterclockwise and 180 degrees clockwise, it's the same thing. So a 180 degree rotation is the same in either direction. So it doesn't matter the direction for 180 degrees. And when it doesn't specify, once again, our center of rotation is the origin. So I'm going to just dot that point. I'm going to do the same process that we did before. I'm going to start with point C. I just picked that one to start with. And our L shape looks like this. So I'm going to imagine turning it twice, 90 degrees and then 180 degrees. So 90 degrees, 180 degrees. And our original figure is in quadrant 1. So our rotated figure should end up in quadrant 3. And this makes sense because if I start here and I go this way and this way, it'll put me in quadrant number 3. So this was 2, 1, 2, 3, 4, 5, 6. So 2, 1, 2, 3, 4, 5, 6. And here I have my rotated point, C prime. So the original was 2, 6. And our rotated one is -2, -6. Okay. Next, I'm going to do point B. And I'm going to take our L shape, just like we did before, and I'm going to rotate it twice. And let me count the spaces. 1, 2, 3, 4, 5. 1, 2, 3. Oops, my bad. 1, 2, 3, 4, 5. 4, 5, and then 1, 2, 3. And that is our rotated point, B prime. So the original point was 1, 2, 3, 4, 5, 3. And now our rotated point is -5, -3. Okay. Next up is point A. So I'm going to take that L shape and I'm going to rotate it twice, 90 degrees, to get 180 degrees. Okay, so now let me count. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And that was 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And that is our rotated point, A prime. So the original point was 8, 6. Now our rotated point is -8, -6. And the pattern continues, as you can see, when we're rotating 180 degrees, the coordinates stay the same, but they become the opposite signs. So D is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the rotated point D should be -5, -9. 1, 2, 3, 4, 5, -9, and here's D prime. Let me connect it together so that you can see the rotated shape. And notice how it is the same figure as the original. It just turned 180 degrees around the center of rotation, which is the origin. We're not going to do this one on the video, but I just want to briefly talk about how you would do it. So 270 degrees counterclockwise is 390-degree counterclockwise rotations. So if it's over here, and let me just draw the clock so that you guys can see it a little bit better. So if right now it is in quadrant number 4, counterclockwise is this way. So it's going to go 90, 180, 270, and it's going to end in quadrant 3. But that's the same thing as doing a 90 degrees clockwise rotation. Because if we take this and we rotate it 90 degrees clockwise one time, it will end up in the same quadrant. So rather than doing 3 90-degree counterclockwise rotations, you can just do one clockwise rotation to take all the points and turn it into here. We're going to do one where the center of rotation is not the origin, and it's going to be the same process as we did before. And we are going to be doing a clockwise rotation here because we didn't do the last one. We just spoke about how we would do it. So what we're doing is we're taking this triangle and we're going to be rotating it 270 degrees clockwise around this point. And just to remind us what the directions are, If we're going clockwise, we are going this way. But remember, 270 degrees clockwise is the same thing as 90 degrees counterclockwise. Because if you have a point in quadrant 1, if you do 270 clockwise, 90, 180, 270, it'll be in quadrant 2, and that's the same thing as moving it one quadrant over clockwise. So rather than do 3 90-degree clockwise rotations, we're going to do one 90 degrees counterclockwise rotation because these are equivalent rotations to each other. So we are going to get started on that one. What I'm going to do is I'm going to just connect from point Z to the center of rotation here. And I am rotating 90 degrees counterclockwise. So the L is going to look like this. So counting the spaces, that is 1, 2, 3, 1, 2, 3, 4. So 1, 2, 3, 1, 2, 3, 4. And that is our rotated point, Z prime. Now, let's connect point Y to the center of rotation. And that L shape looks like this. So if we rotate it 90 degrees counterclockwise, it's going to look like this. So that's 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. So starting at our center, 1, oops, I don't have my line. Oh no, I wanted the same color. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And that is the point Y prime. And then finally, we just have point X left to rotate. So I'm going to connect point X to the center of rotation. And if I'm rotating that L shape 90 degrees counterclockwise, it's going to look like this. So that's 1 over and 1, 2, 3, 4, 5, 6, 7. So 1, 1, 2, 3, 4, 5, 6, 7. And that is the point X prime. And now, if I connect these together, our image points, we have the original figure rotated 90 degrees counterclockwise, which is the same thing as 270 degrees clockwise. And if we take a look, what happened to one of the pre-image points compared to the image point? So for example, X prime is -2, 1, 2, 3, 4, 5. Sorry, that's X, not X prime. X is -2, 5. And X prime -1, 2, 3, 4, 5, 6, became -5, 2. So now let's have the order switch, and the original y coordinate became the opposite sign. So we can fill in our table over here. The order switched. The original y became the opposite sign. So here are the rules for rotation. And now before we end the video, we're going to talk about one more thing, which is mapping a figure onto itself with rotations. So in the first question here, we have a regular pentagon, and we're rotating it clockwise about its center. And we need to find the minimum number of degrees it must be rotated to carry the pentagon onto itself. So here I have a pentagon, and if I turn it, let me go back to 0, so I'm at 0, and if I turn it, it looks like itself again at 72 degrees. So that's the first time it looks like itself. And then it happens again at 144 degrees, and again at 216, and again at 288, and again after it makes a full circle at 360. So every 72 degrees, every multiple of 72 degrees, this pentagon will look like itself. So over here, the answer to the question is 72 degrees. That's the first time that it will look like itself. And we can figure that out by doing 360, which is a full circle, divided by the number of sides and angles, which is 5 in the pentagon, and that gives us 72 degrees. In this next example, we have a hexagon, but it's the same question. It's rotated about its center, and we need the degree measure that will carry it back onto itself. So a full circle is 360. A hexagon has 6 sides and 6 angles. So that is 60 degrees, and that's the minimum number. But that's not an answer choice. But remember, it will happen again. It will look like itself at every multiple of 60. So 120 degrees is the only multiple of 60 on this list. And then finally, we have a decagon. A regular decagon is rotated n degrees about its center, carrying the decagon onto itself. And we're looking for the value of n. So same process, a full circle is 360 degrees. A decagon has 10 sides, and that's 36. So what we need to do is we need to go through and we need to see which of these answer choices is a multiple of 36. And it ends up being 252. 252 divided by 36 works out to be a whole number of 7. And that is the answer here that we're looking for. If we take a look over here, we have the same kind of question where we're talking about mapping a figure onto itself, but we're not talking about rotational symmetry here. Here, we're talking about a reflection that will carry the square onto itself. So I'm going to start with the bottom answer choice first because it looks the most complicated. If I subtract x from both sides to put this into y equals mx plus b form, the equation of the line in number 4 is y equals negative x plus 4. So that means it has a y-intercept of 4, 1, 2, 3, 4, and it has a slope of negative 1. So let me go down 1 over 1 to get another point, and I'll keep doing that so I can get a bunch of points on this line. And notice how this line is a line of symmetry of the square. If we take a look at both sides, it's mirror images of each other. So if we reflect over a line of symmetry, it will carry this figure onto itself. So that's not the answer choice that we're looking for here, because the question is which one will not carry it onto itself. The next one is the line y equals x. The line y equals x has a y-intercept of 0. It doesn't have a y-intercept. And it has a slope of 1. So up 1 over 1, up 1 over 1. I think that's enough points for us to get the idea. And notice how it's basically the same thing as the other answer choice, where it's a line of symmetry, just a positive line of symmetry instead of a negative line of symmetry. So if you reflect over a line of symmetry, it will keep the figure looking like itself. So that is not the answer choice that we are looking for. The next choice is the line y equals 2. That's a horizontal line going through the y coordinate of 2. 1, 2. And once again, this is a line of symmetry. It's a horizontal line of symmetry. If you reflect over a line of symmetry, it will look like itself. So that only leaves one more answer choice, 1. and that is a vertical line through the x-coordinate of 5. 1, 2, 3, 4, 5. So that line will look like this. And if you reflect over that line, you're going to see a mirror image on the other side of the line. So it's going to look something like this. It's going to flip over the line and it's going to move. It's not going to be in exactly the same space, looking exactly like itself. With that being said, we have 2 more examples over here. And it says in the first one, which transformation would not carry this rhombus onto itself? And it does say that the diagonals are not congruent in this rhombus. Answer choice number 1 says a reflection over the shorter diagonal. So let's say this one's the shorter diagonal. That does look like it's a line of symmetry to me. So I'm going to put that one on hold. Number 2 is a reflection over the longer diagonal. But once again, that does look like it's a line of symmetry to me. So I'm going to put that one on hold as well. Number 3 says a clockwise rotation of 90 degrees about the intersection of the diagonals. So 90 degrees, let's give these diagonals values because we know it's a rhombus with non-congruent diagonals. So let's say this diagonal had a piece that was 5 and 5 to make 10. And this diagonal had a piece that was 2 and 2 to make 4. Once again, I just randomly picked those numbers, but I know that they're being split equally because a rhombus is also a parallelogram. And if this rotates 90 degrees, it doesn't, clockwise, 90 degrees clockwise. And I'm not a good artist, but imagine it flipping upwards. So that would be 5, that would be 2, that would be 2, and that would be 5. That doesn't look the same as the original. But the next choice is 180 degrees, so then it would turn again. And if it turned again, just imagine it turning, because it's turning about the center. That would be 2, that would be 5, that would be 5, and that would be 2. And that does look like the original. So this is the choice that we're looking for. And finally, one more. And this one is which does carry the parallelogram onto itself. So not which one does not. This one is which one does. So the first answer choice is a reflection over the line y equals x. The line y equals x looks like this, and that is a line of symmetry. The line y equals negative x looks like this, and that is a line of symmetry here. A 90 degrees counterclockwise rotation about the origin. So here's the origin. 90 degrees counterclockwise. And let me try to draw it on top. Actually, I'll draw it underneath. So imagine this moving up. Once again, I'm not a good artist, but A would go here, T would go here, M would go here, and H would go here. So as you can see, this wouldn't carry it onto itself. But if you rotate it again 180 degrees, if I rotate it again 180 degrees, that would be T, that would be A, that would be H, and that would be M. Still not the same as the original. So these two definitely don't carry it onto itself. So we're between these two over here. So from here, see if you can pick the correct answer.